Good morning or good afternoon to everyone. My name is Leonardo Paoli. I'm an analyst here at the IEA, and I would like to welcome you all for this webinar, which is the first installment of the webinar series following the Energy Technology Perspective 2024 edition. In this webinar, we will be focusing on some of the core analysis that underpins the publication, namely the work on clean energy technology manufacturing and trade. This is only the first webinar of a series that will have 4 webinars in total. Later today, there will be another webinar focusing on the future of shipping, whereas next week, there will be 2 more webinars, one that focuses on manufacturing opportunities in emerging markets, and then another one that focuses on heavy industry, and so on the production and trade for near zero emissions materials. So I invite all of you, if you're interested in these topics, to sign up for these webinars as well. Now, this is how this webinar will run. I will begin with a short introduction about the global manufacturing and trade outlook that we have for all clean energy technologies. And then we will go on to, let's say, the core of the presentation, which is where each expert here at the IEA will go through the technology on which they have worked and will provide some of deeper, let's say, insights for each individual technology. Today, we are very lucky to be joined by Dr. Frank van Tongeren. He is a former head of division in the Director for Trade and Agriculture at the OECD. And at the end of the presentation, he will spend 5 minutes to provide us his thoughts about how this work fits in the overall debate. Thank you very much for joining us, Frank. I would like to encourage all of you to please send as many questions as you have using the Q&A function in the Zoom. We will have time at the end of the presentation to answer your questions, and any question that is left unanswered will receive an email follow-up. Okay, so let's start. I would like to begin by explaining what we mean by clean energy technologies. Here at the IEA, we often refer to these 6 technologies when we talk about clean tech. And there are several reasons. One reason is that these six technologies alone account for about half of the clean energy investment spending of 2023. They are also technologies that are very often mentioned in several policy documents by governments that talk about either trade or industrial policy. They are all mass manufactured technologies that have undergone rapid learning rates over the years and are expected to continue to do so in the future. And they are technologies that account for significant shares of emission reductions in our scenarios. What is the context for this report? So we find ourselves with a change that has happened over the course of this decade, where clean tech has gone from, let's say, a fairly niche market, a fairly niche set of technologies that were worth about 200 billion in 2015, to a major economic opportunity that already in 2023 was worth 700 billion. What has happened in this time is that we've had massive increases in deployment. Electric vehicles accounted for about 1% of all sales in 2015, whereas today they are more around 20%. And the installations of solar PV in 2015 were only 1/10 of what we expect to see in 2024. We think that this growth will continue, and by 2035, under current policies, the market for clean techs could reach $2 trillion. And to give some context, $2 trillion is roughly the same size as the market value for oil in the last few years. It's not just market size that will increase, but it is the overall, let's say, economic world that sits around clean tech. For example, when we look at interregional trade, we see interregional trade to be increasing over the years ahead, more or less following a similar, let's say, proportionally to the market size, so roughly a threefold increase to 2035. And there's 2 main reasons for this. One is that there is a geographical mismatch between some of the production capacity for some of these technologies and the demand that we project in our scenarios, and therefore trade is necessary to reconcile demand and supply. And also, we have noted that there are differences in costs of production for these technologies in different parts of the world. And therefore, as countries seek to have a transition that is as affordable as possible, trade will be a useful tool to increase the affordability of these technologies. When we look at the investment world, let's say the key message is that investments in the manufacturing for these technologies will not be a barrier. We've had a surge of investments over the past few years, and in our projections, let's say the next decade would only require half as much yearly investment in manufacturing capacity as what was invested in 2023. And as we go forward in the second part of our modeling horizon, investment needs decline further as their demand plateaus and sort of growth starts to become a bit slower. Now, before leaving the main presentation, I just wanted to remind you about the way we use scenarios at the IEA and some of our key scenarios. So we have the stated policy scenario, or STEPS. This is a scenario that explores where existing policies will take us, and so it only focuses on policies that already exist, are legislated, and have funding. Then we have the APS scenario, the announced pledges scenario. And this is a scenario that has a different role. Here we are exploring what would happen if all of the announced net zero and other pledges by governments were met in full. This is normally applied to energy and climate policy. However, for the purpose of this report, we have expanded our scenario definitions. When we are looking at manufacturing capacity, we are considering only projects that have reached final investment decision in the STEPS. Whereas when we are considering manufacturing capacity announcements in the APS, we assume that all projects that are announced will be realized by 2030. We have also expanded onto industrial policy. And again, we've applied a similar logic as what was applied for what we normally apply for energy and climate. And therefore, policies that have a clear definition, that are legislated and that have sufficient funding backing them, are included in the STEPS. Whereas policies that are more like, let's say, pledges or look more like targets than fully crafted policies, they are included in the APS. And here in this slide, you see just some examples of how we have made this distinction for three major markets. However, the list of policies that we included is much longer than what you see here. So without further ado, I would like now to give the floor to my colleague Faden, that will bring you to the solar PV world.
Thank you, Leonardo. My name is Faden Papadimoulis, and in the following slides, I'm going to focus on the solar PV supply chain landscape. The solar PV deployment has been breaking records year after year, and the continuation of this momentum is critical both for the CO2 emission reductions on the one side, as well as the energy security of any fossil fuel importing country on the other. As mentioned in the general introduction, there has been a rapid increase in the manufacturing capacity for clean energy technologies in the recent years, and the solar PV has been a prime example and a driving force of this trend. Our analysis in ETP 24 was focused on the following solar PV components going from upstream to downstream and whose facilities are mapped on the chart. Polysilicon, wafers, solar cells, and solar modules. The growth in manufacturing has been observable across the totality of the PV supply chain. However, as of the end of 2023, effectively, all the facilities were concentrated in a limited number of regions globally, and more specifically in China, in other countries of the Asia-Pacific region, in Europe, and in North America. As the distribution of facilities on the map shows, China has by far the biggest share of manufacturing capacity across all the PV components. More specifically, China's shares range from about 80% of the capacity for modules production to around 95% for wafers. Apart from China, the countries in Southeast Asia and India have a strong presence in the PV manufacturing sector, holding the second place in terms of capacity and production, with the exception of polysilicon. The stronger presence of the US and Europe, and more specifically Germany, in the polysilicon segment is related to a large extent with the prior existence of facilities there for the semiconductor industry. Now going to the deployment, it is shown that the solar PV deployment has grown very rapidly recently, with the demand numbers for 2023 being doubled from just 4 years ago. The PV as a technology has achieved this very good momentum, as it is now driven not only by policies on renewable energy, but primarily by its very competitive costs compared to other generating technologies, as in many regions of the world, the solar PV has become the cheapest source of electricity. Therefore, the current demand is expected to continue to grow considerably in the future, and is expected to reach around 670 gigawatts of demand in 2035 under steps, and even more, around 860 gigawatts respectively for the APS in 2035. Despite the anticipated growth in PV demand, the existing manufacturing capacity across the supply chain seems to be able to accommodate on a global scale all of the PV supply chain components in 2035 for steps. Whereas if also the announced manufacturing capacity is taken into account, then it will be sufficient to accommodate also the APS scenario in 2035. However, the overall picture of the supply chain has changed in the recent months with respect to announcements due to project cancellations and earlier decommissioning of facilities in the near future than initially anticipated. This change has been the result of the relatively high current manufacturing capacity in conjunction with the low prices at the moment, which put pressure on manufacturers. Indicatively, the modules were being sold in the recent months at slightly over 10 cents per watt, which is less than half of what was the case at the beginning of 2023, with some manufacturers selling at a loss, and a large part of the production in 2023 and 2024 absorbed by inventories. This overall picture has already initiated a consolidation process in the industry, which is not unusual in new sectors. The consolidation has been more visible in the wafers and polysilicon segments, where the projected manufacturing capacities were revised downwards by 1/5 at the end of the second quarter of 2024 compared to the first quarter of the same year. These segments of the supply chain have lower profit margins than the more downstream parts, so any company that is vertically integrated will be better equipped to weather the storm and come out stronger from this consolidation process across the chain. Having now a closer look at the fundamentals of production costs, the total final cost of a PV module, that is to say, from start to end, which means from the polysilicon production to assembling of the modules, and by excluding, of course, any profit margin in between the steps, is coming at around 80% from variable costs and primarily from the materials and energy inputs. The fixed costs, like the capex and fixed opex, contribute to around 1/5 of the overall. By looking in greater detail into each step of the supply chain, the majority of the material costs come from the downstream components of modules and cells, whereas the most energy-intensive production of wafers and polysilicon accounts for the majority of the overall energy costs. From a regional angle, China is the most competitive region in producing each PV component separately, when, of course, excluding any explicit financial support to the production, like the US Inflation Reduction Act that we have taken into account also in our model. The relative costs for producing the PV components depend on the cost of inputs, where any cheaper inputs that the Chinese manufacturers might have access to, like cheaper energy or cheaper capital compared to other regions, contribute to the overall competitiveness. However, the Chinese competitiveness is related also to a great extent to the vertical integration of the supply chain, to the access to skilled manufacturing labor, and of course, to the economies of scale which are derived from the very large facilities. On average, the Chinese facilities are much larger than those in other parts of the world, and their sizes keep becoming even larger with time. Just to give an example, China's largest solar module manufacturing facility, currently under construction in the Shanxi province, could alone produce enough modules to cover virtually all of the EU demand today. All of the above come together and synthesize the current landscape of the solar PV manufacturing supply chain, with China having a very strong presence vertically. China is the biggest demand area and at the same time the biggest exporter. It is exporting primarily solar modules as the final product to almost every region, and to a lesser extent wafers and cells, mostly to Southeast Asia, as it's needed for their domestic manufacturing of cells and modules respectively, a part of which of course, is operated by PV companies headquartered in China. The only exception to China's module exports is North America, where the US, which drives the demand, has implemented a set of measures like import tariffs towards China, which have directed any imports to the Southeast Asia and India as of 2023. In the future, and according to the current policies shaping the STEP scenario, China is expected to remain the #1 producer and exporter of modules and other components. However, the future landscape will not be shaped only by China. As more countries implement industrial policies, new local manufacturing capacity for domestic production is anticipated to come online. The Inflation Reduction Act in the US and the Production Linked Incentive Scheme in India have already started boosting the domestic capacity in these countries with their financial support, and will continue to do so in the near future, so that in 2035, the modules production is expected to be accommodated completely domestically for these countries. As it's relatively more accessible to establish manufacturing for the downstream components, we expect more diversification to be achieved in the modules and cells, with Chinese exports effectively being shifted further upstream. A similar picture, but even more pronounced, takes place in the EPS scenario. The global demand is higher due to the climate pledges, but similarly, there's an embedded higher ambition for clean tech manufacturing and any respective industrial policies that support it, which leads to more regions being part of the manufacturing supply chain. And with that, I'm passing to my colleague Matilda to talk about wind, which the other renewable electricity tech covered in our report.
Thank you, Fedon. Before I start with my slides, I just want to highlight that in the wind supply chain, there are many, many components, but in the report, we only touched upon the nacelle assembly, blade manufacturing, and the tower manufacturing. So the global manufacturing capacity for nacelles, I'll start with that one, amounted this year to 180 gigawatts at the end of 2023. And the production totaled about 125 gigawatt over that year. Most of this capacity is in China, as you can see on the little dots and in the pie chart on the left, with about 60%, and Europe being the second largest producer with 50%, and these shares kind of roughly match where turbines are installed these days as well. Overall, we see that nacelles is the most regional concentrated component for the wind supply chains. I'll show you later on. But its regional concentration is much more diverse as compared to, for example, solar PV, which we saw before. Then moving on to blades, we see that more countries are also having manufacturing facilities for these components. And for example, we see South America, Mexico, Turkey, and Australia also having facilities for these components. And this is due for two reasons. The first one being the extra transport costs for these larger components. So nacelles are very big, obviously, but blades and towers are even more big. So these will be more expensive to transport to the wind farms. So that's why we see that, these facilities are installed locally more. The second reason being that, especially blade facilities, they are cheaper to actually set up than nacelle facilities. Nacelle facilities require lots of other manufacturing industries close by, so to produce other components, while blade is more in a compact process to manufacture, even though it's very complicated, but maybe less complicated than nacelles. The tower facilities, here we see that the share of China where things are produced is less than 50%, which is 15% less than the nacelle share of China. And we see even more countries taking part in this part of the supply chain for wind. Then moving on to the demand. So in the recent years, we saw, that 2023 was another higher year than before, with deployment of turbines reaching about 125 gigawatts. And this was mainly in China and in Europe, as we saw before as well. In the STEP, we see this demand increasing by 1.5 times by 2030. And in the APS, this is double the amount as we have today. And it's good to mention that, China's absolute number is decreasing, but also its share is decreasing, while Europe, other Asia, and North America are increasing a lot their demands on their STEPs and APS. Another thing to worth mentioning is that the onshore sector, which is not shown here, but the split between onshore and offshore is changing rapidly. In 2023, we had around 10% being offshore, but in 2030, this will be around 25%. So lots of changing in this industry. This increase in global demand will require manufacturing capacity expansions. As we saw today, as we saw on the slide before, mainly China, Europe have lots of manufacturing capacities in place already to provide their own demand and other regions. If all capacity is utilized that we have today to the full extent, then we see that only China will reach its 2030 the peak demand, whereas other regions have a bit of a gap, and they won't be able to reach this. So we mean that OEMs, they need to announce more capacity additions, and there have been some announcements. We see many of these announcements happening in China, so they're very much rapidly expanding all of their subcomponents in these regions, but also Europe and the US have significant announcements, but still not enough to reach these these targets and these forecasted demand additions. So this means that there's a bit of a lag, but we also see that like if you compare to solar, the announcements they will come if demand is secure and stable. So if OEMs see that wind farms are happening, that the permits are made, that it's very secure and they can start making new additions to their manufacturing capacity, then this will follow very rapidly after. So it's not a bottleneck, but it's definitely, we expect more announcements than just these if this demand is met. So they go hand in hand, basically the announcements and the demand, which is a bit different than solar components. So what drives the wind manufacturing production cost? And what does it drive, but also this drives where it's made. And looking at the cost of components across the supply chain, we see that nacelles and towers are the costliest to make, while blades are a bit less expensive. The main contributor of the production cost is the materials. This is materials such as steel, fiberglass, and carbon fiber, which you need to think about, but also some part of critical minerals, which also are quite expensive. The second largest part is the components, and this shows up here because we have analyzed the nacelle assembly manufacturing capacity. So components such as gearbox and drivetrain, they're quite expensive in this view, so they show up as the second largest contributor to the production cost. The regional diversity between these regions that we analyzed, we see that China is the cheapest, and Mexico for blades. And this is what you would expect. You also see India being very close to China in production costs. And India, Mexico, they're all kind of production hubs already for, well, Mexico for blades, but India for blades and nacelles. We see that the US and Europe are more expensive than China and these other manufacturing hubs. And this is all for nacelles and blades, and for towers, we see everything quite close. And there's also different schemes in the US. There's, for example, the IRA, which kind of pushes this price lower to China. So we think it's a very attractive place to manufacture under the IRA these kind of components. And this is again kind of saying, like, if demand is secure, then these regions could be attractive to start manufacturing facilities. But as they go hand in hand, we suspect that these things will pop up more. Then, so we know more about the production costs, we know more where current facilities are, and we know where demand is. So now we can look a bit about the global picture of the trade today. As mentioned before, China is the biggest deployer of turbines. They're also the biggest supplier. So right now we see this big block of China. Also Europe is the second largest producers of turbines components, and we see that they are mainly importing nacelles, which is, as said before, they are kind of lighter, so they're easier to transport, and they will be more traded than compared to blades and towers. Then moving on to steps here, as said before, the demand of China is going to decrease a lot, and instead it will export to other Asia and Europe. will also import a bit from China, but we'll see that they also ramp up their manufacturing capacity as do North America. So trade will remain about the same, but other Asia will definitely increase imports from China as their demand is also increasing a lot. And we also see again this kind of tendency to have nacelles being more traded as opposed to blades and towers. In the APS, we see a similar trend. So even the demand becomes even larger than the other regions and the share of China becomes smaller. The only thing is that in Europe, their own demand becomes much higher than steps, obviously, and that's why they don't have the capacity to export products as in steps. So here we see that, North America and the rest of the world, they need to also get more components from other Asia and China. And I will leave it at that. There are many cases in the report where you go more in depth in all of these different regions. So I invite you to read more on there. And I'll hand over to Theo about electric cars.
Thank you very much, Mathilde. I'm Theo Lombardo, and together with my colleague Jules, we will unfold for you some of the key results for electric cars and battery in this case. And starting from the situation today, the geographical concentration of manufacturing capacities varies greatly across the EV supply chain. 2/3 of manufacturing capacity to produce electric cars was located in China in 2023, which is about in line with sale. China accounted for 60% of the world total in 2023 sales-wise. But large capacity to produce electric cars, however, also exists in Europe and the United States, thanks to their important role in car manufacturing globally. And there are also several plants in other countries or regions, such as India, Southeast Asia, Brazil, and Morocco, among others. But things change markedly when looking at plants to produce batteries and battery components. So if we move on batteries and battery cells in particular, production facilities are mostly concentrated in China, accounting for over 80% of global capacity, even though large production centers exist also elsewhere, such as LG Energy in Poland and Panasonic in Nevada, United States. Well, when you look at components, key battery components such as anode and cathode active materials, manufacturing capacity is even more geographically concentrated. In 2023, almost all capacity for those components was located in China, with some share of cathode capacity in particular that was located in Korea or Japan, thanks to the presence of domestic leaders in battery manufacturing in those countries. When we look at demand and how demand is projected to evolve over the next decade, from today to 2035, China is set to remain the largest EV and battery market. Under current policies, total battery production grows over 7 times, reaching more than 6 terawatt hours, thanks to rapid growth in electric car production that is today and set to remain the largest source of battery demand, but also growing demand from other sectors, such as electric trucks and battery storage. During this period, battery demand diversifies, but remains strongly concentrated in today's largest electric vehicle markets that are China, the European Union, and the United States. They together account for over 3/4 of global demand in 2035, down from about 85% in 2023. If we move from steps to APS, so if all announced policies are fulfilled, battery demand will grow and diversify even further. In this scenario, thanks to transport electrification strategy that boosts electric vehicles demand in emerging markets and developing economies outside of China, their share of global battery demand grows significantly. It grows over 6-fold, reaching about 20% in 2035 from just about 3% today. From a global perspective, if we look on the supply and manufacturing capacity in particular, battery and battery components manufacturing capacity is said to be ready and sufficient to serve our climate ambitions, and they are not expected to represent a limiting factor for growing EV and battery demand. However, we do expect a certain degree of consolidation that is due to a high level of competition, in particular in markets such as China. And to give a sense of scale, demand in 2023 that was about 850 gigawatt hour was just 1/3 of global manufacturing capacity in the same year. So again, very strong competition there. When we look at production and trade today, China is by far the largest producers and exporter for all steps of the EV supply chains. The European Union and North America are anyhow, already today large EV and battery manufacturer, albeit smaller than China, and they do serve part of their domestic EV demand. While we do have also countries like Korea and Japan that are the second largest source of battery components. They, of course, produce also batteries and EVs, and in particular, they produce then also cathode active material. If we move from today to 2035 under current policy settings, electric car demand grows more than 4 times and reach almost 60 millions, and the share of Chinese electric car production decrease over this period of time, mostly thanks to investment in EV and battery production in North America and the European Union. However, there is little diversification for battery components, which is almost all produced in Asia, and the large majority of which in China. If we go to APS, in 2035, we will have a much more diversified supply chains, thanks to largest EV production in Europe, but also largest EV and battery production in Asia outside of China, notably in India and Southeast Asia, but also in North Africa, also thanks to local resources as critical minerals or materials to produce batteries in particular. Global production will also grow further to satisfy larger demand. It will reach 70 million electric cars and almost 8 terawatt-hour of batteries in 2035. And with this, I leave the floor to my colleague Jules, that will have a deep dive on the European Union as a case example, but I also advise you to look in the book for many other analyses on different regions.
Perfect, Theo, thanks. So I'd like to delve into the case study of EV and battery trade involving the European Union. In 2023, electric car sales in the region reached about 2.3 million, or almost 1/4 of all car sales in the region. While EU-made electric cars accounted for the majority of domestic sales, we saw that 1 in 5 cars sold in 2023 was manufactured in China. However, more than half of these Chinese imports to EU were made by car makers headquartered outside China, such as Renault or Tesla, that are currently taking advantage of the low manufacturing costs. On the right-hand side chart, we show that in the same year, almost half of the EVs produced in Europe were equipped with locally made batteries. And while investments and announcements have been made in the sector, the local production of cathode and anode active materials was nonetheless almost zero, as sizable local manufacturing capacity is not yet established today across the Union. Moving forward in the step scenario, EV imports from China are expected to account for about 40% of the EU domestic sales by 2035. This increasing share of Chinese imports is driven by the projected competitive Chinese EV prices, resulting from their low-cost manufacturing of EVs and, most importantly, of batteries and electric powertrain components. If we now shift our focus to the battery manufacturing side, we expect that more than 2/3 of the sold batteries will be made in the European Union by 2035, and manufacturing capacity is not expected to be the limiting factor here. Indeed, utilization of the battery manufacturing capacity in the EU is limited by the amount of EVs produced locally, as they are the primary driver of battery demand. As a result, the reduced local EV production will drive the decrease in battery demand that in turn will affect the utilization rates of battery plants. Additionally, China's competitive battery manufacturing is expected to secure some imports to the EU, accounting for up to 25% of local demand. And further right on the charts for cathodes and anodes, the lack of investments is projected to limit the domestic production, in turn reducing the domestic share in battery active material production. If we now focus on the APS, where we investigated the impact of stronger manufacturing support policies in the European Union, such as the NZIA, if such policies would be adopted, we estimate the share of local production in EU electric car sales to increase to 70% by 2035. On the battery side, we expect to see a significant increase also in local production, with about 90% of the battery cells sold in the European market being produced locally. Additionally, with this NZIA supporting partial onshoring across the battery supply chain, the EU is projected to meet up to 50% of its cathode demand and 40% of its anode demand by 2035. If we now take a closer look into some of the main drivers behind the projected Chinese imports to Europe, meaning the EV and the battery manufacturing costs, we see that for a representative electric car segment, we estimate that today the Chinese-made EVs are about 20% cheaper to buy on the EU market than their locally produced counterparts. In the battery segment of the supply chain, the European Union is even less competitive, with manufacturing costs for battery cells and cathode active materials estimated to be over 30% and 40% cheaper in China, respectively. And to bring back a level playing field in the EV markets between domestic and Chinese car makers, the EU has adopted new countervailing import duties on battery electric cars made in China. This decision followed an investigation into the alleged financial support provided by the Chinese government to EV manufacturers and resulted in company-specific tariffs taking effect in 2024, this year. With such tariffs, in the right-hand side of the chart, we estimate that on average, an EV made in China will remain competitive with its EU-made counterpart. However, over the 5-year period during which these tariffs will apply, they are likely to increase the average EV price if EV makers choose to pass on the additional costs to the consumers rather than absorbing them within their margins. Now, also, if these tariffs aren't designed carefully and if they stay in place for too long, the EU risks missing a critical opportunity to boost the competitiveness of European car makers. So it's a delicate balance. We need to avoid giving local manufacturers too much of an advantage because competition is key. But it's competition that may help drive down EV prices and make them more accessible for everyday consumers, ultimately fostering the transition to electric cars. And with that, I'll hand over to my colleague, Chiara, who will talk about heat pumps.
Yes. Thank you, Jules. We will now discuss heat pumps, are technologies that play a central role in the global transition to secure and sustainable heating. And in this presentation and analysis, we will focus on heat pumps that are used as primary heating equipment in buildings. Heat pumps are not mainstream at the moment, but they've been receiving increasing policy support in several countries over the last years. And this led to record sales in 2021 and 2022. However, in 2023, sales stalled. And in the first half of 2024, we are seeing a decrease globally of 10% compared to the same period of 2023. The decline in sales was mostly driven by a sharp decline in Europe. And overall, major markets for heat pumps today are China, North America, and Europe, followed by Japan and Korea. When we look at the manufacturing capacity, heat pumps manufacturers are less geographically concentrated compared to other clean energy technologies, mostly reflecting demand patterns, and only about a fourth of production is traded today. This is partially explained by the fact that heat pumps are adapted to local conditions, and local heating equipment manufacturers are already familiar with local preferences, but also with local standards. Moving forward, even under current policy framework, we do expect a pickup of heat pump sales in the years to come. For instance, if we think at increasing competitiveness with alternatives, and also at energy efficiency regulation in buildings. In the STEP scenarios, heat pump sales more than doubled from 2023 to 2035, mostly in major markets. And in terms of manufacturing, we see here that there is no significant change in the geographic concentration of supply. Deployment is even faster to meet climate pledges. In the APS scenario, heat pumps become the dominant heating technology globally. Some emerging markets that do not have an established industrial base today will remain small markets, but they will see an increase in demand, and this can create opportunities for other markets to expand their exports, particularly China, but also some major cooling markets such as Mexico and Southeast Asia, for instance. For both the STEPS and APS scenarios, sustaining high production volumes is critical to ensure competitiveness of production costs, but of course with some different considerations across regions. If we look at China, China today is around 40% of global capacity and about half of global exports of heat pumps. It has favorable business conditions, for instance, looking at the access to cheaper skilled labor, infrastructure, and also when we look at the supply chain, so production of components such as compressors, as well as refrigerants. China can also build on the large manufacturing capacity for air conditioners that can ramp up quickly. And this leads to a levelized production cost that today is around 35% lower than the world average. Chinese manufacturers are also increasing investments in research and development, with Chinese patents more than doubling since 2010, and this could pave the way to meet stricter energy efficiency standards. In both our scenarios, for these reasons, China maintains its leading role in manufacturing and exports of heat pumps. If we look at the European Union, it is the world's third largest market, both in terms of manufacturing capacity, but also in terms of installed capacity. The European Union has a strong track record in research and development and innovation, in particular lead the world in segments such as large-scale heat pumps and hydrocarbon refrigerants. It also has a clear legal framework for new construction and renovation plan, which is quite unique. Also unique, where we announced investments in new heat pump factories that totaled over $3 billion over the last 3 years. Those type of announcements are very uncommon for heat pump manufacturers elsewhere. And if realized in full and on time, these additions would more than double capacity between 2023 and 2030. Although the recent slowdown in heat pump sales that we observed in 2023 and early 2024 is posing doubts over the realization of some of these investments. And achieving the European Union climate ambition for heat pumps, for example, if we think of the Repower EU Green Deal for 55, will really depend on the concrete, mostly national policies that are introduced to reach these targets. And last, an overview of the United States. United States is currently dominated by large centralized units using ducted systems, and these systems are less common in other markets and are mostly produced domestically. The US is the second largest producing country at the global level and is also like to remain so moving forward. In the STEPS scenario, financial support to manufacturers under the IRA pushes up domestic production, although capacity does not fully keep pace with domestic demand growth. In the APS, more stringent energy efficiency policies feed smaller air-to-air units, increasing their market share, and so do imports from Mexico. This last is the lowest cost producer of those units among North American countries. And with this overview, I leave it to my colleague Francesco for electrolysers.
Thank you, Chiara. Another clean energy technology that we have included in our modeling and analysis are the electrolysers for the production of low-emission hydrogen. In fact, low-emissions hydrogen is an important option for reducing emissions in heavy industry, in refineries, but also to produce synthetic fuels for aviation and shipping. And indeed, electrolysis is a critical technology to be deployed for this purpose. Electrolyser manufacturing reached 25 gigawatt per year of assembly capacity in 2023, 60% of which was in China. And this is set to continue to dominate the sector also in the short to medium term. Europe and North America account respectively for 18% and 15% of global capacity. This capacity, though, is underutilized as the demand for electrolysers, both water electrolysers and those used in the chlor-alkali industry, amounted to about 2.5 gigawatt in 2023. The demand was mainly concentrated in China, as you can see from this chart, where several large-scale projects for electrolytic hydrogen production are moving ahead and are being constructed. Operational manufacturing facilities today are located in those regions where the majority of the demand comes from, hence the trade has been pretty much limited so far. This could change in the future, as I'm going to show you in a while. Based on companies' announcements, electrolyzer manufacturing capacity could reach more than 160 gigawatts per year by the end of the decade. China could account for almost 1/3, Europe for 1/5, and about 10% has been announced without a specified location. While the potential output from this announced manufacturing capacity would be enough to supply the demand in the APS scenario by 2035, its full deployment is still uncertain. Almost 100 gigawatts of potential output have not yet reached a final investment decision, of which 40% has been announced without a starting date. While, as I said, today the interregional trade of electrolyzer is very limited, with the demand being supplied mainly by local manufacturers, this could change in the future with growing demand on one side, but also new facilities being announced. In the steps where only committed manufacturing projects have been considered, China dominates the trade market. By 2035, about 45% of total demand is traded, virtually all exported by Chinese manufacturers, to regions where the demand grows, but where there is not manufacturing capacity. Europe and North America supply their market thanks to the existing capacity, with a small share of imports coming from China. When we look at the IPS, demand grows almost ninefold by 2035 compared to steps, while the trade grows only 4 times, representing around 1/5 of the global demand in this scenario. China keeps dominating the interregional trade market, but in this scenario, there is more domestic production in regions such as the Middle East or other parts of Asia, where the demand for electrolyzers grows substantially, and so opportunities for domestic manufacturing. There are some developing economies that are starting to stimulate the development of the electrolyzer industry. For example, in Chile, the government's call for electrolyzer manufacturers to establish facilities in the country has received interest from several companies with plants of about 0.5 to 1 giga per year of capacity. And India is another interesting example. In fact, based on our bottom-up cost modeling, manufacturing electrolyzer domestically in India could be more competitive than importing them from other regions, including China. This is mainly due to import costs, which account for about 1/3 of the total cost of importing an electrolyzer to India, while Chinese imports in general are the cheapest options for many developing countries. In the case of India, this could open the possibility to develop an internal market. When we look at the disaggregated cost of manufacturing an electrolyzer stack, we see that CapEx and fixed OpEx represent a big part of the cost at 40%, and materials account for another 40%. And hence, the measures to support manufacturing are important to the scale-up of the market. As part of the National Green Hydrogen Mission in January 2024, the Indian government announced the SIDE scheme, which provides financial support for domestic electrolyzer manufacturing, but also for the production of renewable hydrogen. There's been 2 tenders during 2024 that selected companies, both Indian-based and foreign companies, for a total of 3 gigawatts per year of manufacturing capacity. And if all these plans move ahead, that would be more than the currently committed plans for new facilities in India. In fact, from less than 1 gigawatt per year of installed capacity today, the manufacturing capacity of electrolyzer in India could grow to more than 3 gigawatt per year by 2035 in steps, so aligned with the tenders I just mentioned, and about 8 gigawatt per year in the APS, part of which could be used for the export market. The announced new capacity instead amount to about 11 gigawatts per year, but only less than 10% of these has reached the final investment decision, hence leaving uncertainties on the future deployment, but also underlining the importance that policy support plays for this nascent market to build up. And with that, I hand over to my colleague, Leonardo. Thank you very much, Francesco, and thank you to the whole team that has worked on this report and presented the results today. I just would like now to leave the floor to Dr. Frank van Tongeren, that will hopefully give us some of his thoughts on this work and how this fits in the overall debate. Really looking forward to these comments. Thank you very much.
Yes, well, hello, welcome everybody, and thank you very much, Leonardo and colleagues, for your very effective and efficient presentation to talk us through some of the highlights of this very detailed report that you have produced, underpinned by enormous amount of knowledge about these technologies and the manufacturing processes and so on, of which we only saw the tip, I think, of this proverbial iceberg in your presentation. I think participants, people who have joined in this webinar will agree with me that we're really privileged to have this little peek in the kitchen where all this is produced. Now, you paint a rather optimistic picture, huh? So tripling of the market size not so far from now, which is encouraging, interesting, and it seems that these technologies, they are now markets in their own. It's not just nice things to have, but there are market opportunities in their own, economic opportunities there to be exploited. Although still much of that opportunity is driven by policies, and I will say a bit more on this later on. Now, concentrating a little bit on the trade side of things, your report shows that, well, first thing everybody will have noticed is China is big and will remain big, but as other countries step up production of these technologies that are considered in this report, the relative size of China shrinks a little bit. It differs across the technologies that you have been discussing right now, but by and large, new kids on the block, new players means that, and greater volumes from them means that relative size of China is shrinking. This also means this development of manufacturing of cleaner technologies elsewhere, that trade flows will be changing. So we have both changes in the existing trade flows, some more, some less, but also new trade flows coming up that you are able to identify. So some of the trade between China and Asian countries, for example, in wind turbines, or the last one on the electrolysers, where you project upcoming trade and production in the Middle East. So that changes, but also the type of energy trade changes. So the nature of the trade changes. Why? Shifting away from fossil fuel trade means that we will see relatively less of this trade that is a more or less continuous flow of imports of fossil fuels being replaced by trade in manufactured goods. So it's completely different types of transport, of course, different routes, most probably with their own challenges, but less of a continuous flow and more trade of manufactured products that are once installed then, and they stay there for a great many years. So the nature of trade is going to change with these developments that you are sketching. It will also have an opportunity, an impact on the trade and services, and let me try to explain that a little bit. So you paint very convincingly the picture that the manufacturing of these technologies is picking up across the globe, which brings opportunities for jobs, job creation. That is important. But this cleaner technology will also create jobs, not just in manufacturing, also in services, which is not so maybe so evident. But what I see there is services not just in installation and maintenance, but also in engineering and design of installations. So this will be another factor, let's say, a positive factor contributing to our economy. So more jobs in energy-related services. Now, this I would reckon will have an impact also on trade in these services. Think about engineering services that can happen in one country but are used in another country. So trade in engineering services across borders related to these cleaner technologies. Services trade up. It already is a big component of global trade, and it can grow even further with this energy transition. Now, finally, let me make a note on policies and trade policies in particular. So your presentation in the report shows that this cocktail of policies, climate policies, industrial policies, and trade policies is very important, has been important, continues to be important for this energy transition. But not all of these policy levers somehow point in the same direction. And probably more can be had by making policies more coherent, aligned better. Trade policies in particular, I mean, when you discussed the electric vehicles and batteries, you mentioned the newly installed countervailing duties of the European Union against China. This is one thing where kind of an industrial policy motivated trade policy is not completely in line perhaps with climate objectives. Another question mark clearly relates to trade policies related to these rather complex value chains that underpin the functioning or the manufacturing. So many of these parts and parts and bits that go into these technologies, they have to cross borders multiple times before they are finally ending up in the final product that gets installed somewhere. Now, reducing barriers to this trade will be very important, I would reckon, to make to realize these ambitions and to realize the scenarios that you're painting. Think, for example, about some of the raw materials that go into these technologies. Raw materials trade is very much hampered by export restrictions on those. That makes them more expensive and limits access. But also, I was just thinking about fossil fuel subsidies. If those would be addressed and would come down, the relative cost of cleaner technologies would look even better relative to fossils. Now, finally, of course, I can't resist a question that's for discussion, and that relates to further import barriers, especially import barriers that are in discussion in the United States. Now, if that would materialize, what would that mean for your prospects? In particular, if indeed the US were to levy higher tariffs against China, what could that mean, for example, for diversion of products onto the European market, and how would that impact, let's say, the viability of some of the European projects in cleaner technologies that are now in the pipeline? Now, this is of course all speculative. Tariffs are not in place yet, but it may still be interesting to reflect a little bit on that. So let me finish there and just let me say thank you again for that work that you have done and the very efficient and effective presentation that you have done today. Over to you.
Very much, Frank. Really appreciate it. Really sort of very good ideas. Or the idea of expanding also the way of thinking, not just to goods but also to services, is definitely something that would be really interesting to explore further. Just as one example of the many things you mentioned. Now we are on to the Q&A session. We have received already some questions from the audience. We're just going to pause for about 30 seconds, and then we will come back and start answering the questions. In the meantime, feel free to ask anything you would like to using the Q&A function here in Zoom. We'll be back in 30 seconds. Okay. very much. We are now back. So we have a first question which relates to the manufacturing, so the role of PV manufacturing in Africa specifically. And this question will be answered by Phaedon, since it's on solar PV.
To begin with, thank you for this question on the role of Africa in solar PV manufacturing, which of course can be extended in general to clean energy technology manufacturing. Of course, Africa has a great potential, and we anticipate big growth in terms of PV installations in the near future, which means that there's a big domestic market. However, this is not, we don't see in the immediate future to be followed by manufacturing respectively, even though there is some small manufacturing which is not shown in the slides just because it is bundled with the rest of the world. But in any case, it is dwarfed by the local deployment. One important thing about the solar PV is that with respect to the range of clean energy technology products that we're dealing with is rather the more homogeneous, we could say. That's to say there's less opportunity for niche, for diversification in niche markets, and therefore regions and countries that have already a head start and have managed to develop economies of scale have drawn the cost down, and the cost is paramount, is a decisive factor for that kind of markets. So for example, Southeast Asia, which has already a strong presence in the field, is better positioned in the context of emerging and developing economies for solar PV across the supply chain. In general, as you saw in the presentation, not only in Africa, but also with respect to Latin America and South and Southeast Asia, the global manufacturing and the global investments account for less than 5% of the amounts on a global scale. From our side, we don't think that this is fair. So for this reason, in the report, we did an analysis where we tried to identify the enabling factors for emerging and developing economies to and the opportunities that they might have for developing their clean energy technology and manufacturing supply chains. In this context, we mapped more than 60 indicators for various countries in Africa, Latin America, and Southeast Asia, which include, among others, the business environment, the transport and energy infrastructure, the resource availability, and of course, the domestic markets. And we undertook a bespoke analysis, and we created a composite index so that we provide a kind of ranking and a good guidance for the policymakers in these regions. Specifically for Africa, we identified as key areas with opportunities of developing and stepping in the clean energy manufacturing that is developing, the battery industry, and this is because the existence of raw materials provides a comparative advantage compared to other regions. In the automotive industry, as there is already an existing manufacturing, particularly in North Africa, and therefore this creates opportunities for expanding this further, and also for the production of steel by using a capacity such as the local iron. For this and more details on that, though, I would like just to take again the opportunity and to invite you to the webinar on the 3rd of December that is handling specifically the manufacturing opportunities for emerging and developing markets. But of course, and one final point is, and since it was mentioned, the finance coming from COP, it's a difficult work for the policymakers in Africa, for every policymaker actually across the world, to balance various, of course, sometimes competing and sometimes aligned targets, like, of course, fostering the domestic industry, manufacturing industry, but also not slowing down the deployment of clean energy technologies and in general of the clean transition.
Excellent. Thank you very much. So now we have a second question, and this is related to the battery industry. And the question is about whether we see potential limitations to the growth because of raw material supplies, and which materials will be, or let's say can be, the bottlenecks, is what was asked. And I think this is mostly relevant to the batteries, as mentioned earlier. So I will let Theo reply to this question.
Yeah, thank you, Leonardo, and thank you very much for the question. Critical minerals is indeed a very hot topic all the time we discuss batteries. And indeed, critical minerals such as lithium, nickel, and cobalt are very important for battery production, but we should distinguish between how much of these minerals we have on the Earth crust, or how much we can extract profitably, so the reserves, and how fast we can mine and process those. From the perspective of reserves, there is no problem for any of these critical minerals. We have much more than what needed. The challenge could arise on the speed of projects for mining and refining. In particular, the thing that we see today is that there are certain critical minerals that are expected to remain well served, and others that need a ramp up of investment. So in the next few years, we see all market being well served, but we see significant gaps between the demand in 2030 and the potential supply for minerals like lithium and copper. For lithium, we have seen already very fast ramp up of production. There's a smaller production, so that should, we expect these to be easier, while for copper is more challenging because it's already a very large production. It's a metal that is already mined at a very large scale, while we do see the market to remain well supplied for minerals like graphite or cobalt, and small gaps for nickels that, however, again, we are convinced can be filled. So these gaps can be filled with proper investments that, however, need to step in now to ensure our production in 2030. And lastly, I think it's also very important to underline that while ramping up rapidly, we need to pay attention on the environmental, social, and governance standard to increase over time, to decrease local environmental impacts on local communities and biodiversity, even though the overall environmental benefits of EVs and batteries is already today very large.
Thank you very much, Theo. So we then received two other questions that relate a bit, let's say, in general, to the prospects for EU manufacturing and for batteries and EVs, and how this relates to some of the recent news that we've heard from, say, the bankruptcy declared by Northvolt. So maybe here we can have different answers. So I would maybe ask Jules to start with an answer, and then Theo, you might complement if something is specific. Thank you very much.
Yeah, thanks, Leo. I could first touch upon with this Northvolt question, and how could it be seen as a threat to the European battery industry? First of all, overall, we do not think that these project cancellations are a threat to the transition, and we don't think that this would contradict our scenario. As we've seen in the slide, there is more production capacity globally in the pipeline than the demand we expect, even in APS, and consolidation is part of the business cycle, but the overall market trend is one of expansion. The Northvolt crisis is a bad blow, for sure, for the European battery industry, but it is not the end of the battery production in Europe. And even before this crisis, the European companies accounted for about a quarter of the announced battery capacity in Europe to 2030, and half of it came from Northvolt. But the Chinese and the Korean companies accounted for more than 50% of it, indicating that we still have much leeway to supply the future battery markets in the European Union. That was for the battery part. I don't know if Theo, you want to add to this?
Yeah, maybe just adding a couple of small points. As Jules raised rightfully, Northvolt was the biggest European manufacturer, but there are many other projects being announced in Europe, so we do expect production to continue there. But battery manufacturing in Europe is indeed reaching a make it or break it moment, and this is the time in which production should really start to scale up, yields should start to be higher, and manufacturing cost to be lower, to become more, to decrease the cost gap with manufacturing production in China. And this relates to the build of the entire supply chains for batteries domestically or located in Europe to decrease costs. So we go from battery and EV production to components and the production of machineries to make those components in batteries, but also on the on aligning or facing the different trends that the industry is facing in terms of innovation and chemistries as well, with the current shift towards cheaper LFP batteries that are mostly coming from China, that are the dominant chemistry there, that can play a significant role, because there are certain OEMs that are moving towards LFP to decrease manufacturing costs, but LFP is really much a domain of China today, while NMC is the chemical of choice in Europe. So there are also some movement on that side to decrease manufacturing costs, but also align with different trends to remain and become more competitive over time. That's really the big challenge European battery manufacturing is facing today.
Thank you very much. So I think now we have the just time for a last question, or rather, there's a set of questions. We received 2 questions that relate to the different policies and different trade barriers that are currently in place for clean tech, and how these affect our scenarios. So I will reply to this question. So we have considered, let's say, a set of different trade measures. We have looked at all of the different customs duties, all the different tariffs that are in place for different technologies, and these are very often different depending on the bilateral partnership that we're looking at, and they're different for each different technology that is considered. We have also included what are normally referred to as non-tariff measures. And these are a set of different regulations and standards that might be not harmonized across countries, meaning that they result in an extra cost for trading a given technology abroad versus in a domestic market. We have considered these by using some academic papers and some different modeling that has converted these NTMs into tariff ad valorem equivalents. And so we've tried to use this information to really try and paint a picture that is as clear as possible, so as realistic as possible of today's trade patterns. There are other trade policies that are included. So, for example, the carbon border adjustment that will soon be fully operational in the European Union. This is also being taken into account, and we've tried to model this as well as we could. But what this affected the most were mostly the material and the net zero emission materials, more than the technologies. Now, what is the impact of all of this? So, to give some senses, we have for many technologies, or rather, let's say for those that are very cheap, so something like solar panels, trade measures can account for about 20% of the cost of what is of an imported module. So these trade measures do have a significant material impact on the costs of the transition. And of course, any effort that it could be taken to decrease these would make the transition more affordable. We are also observing that tariffs on clean techs are very often much higher than they are for fossil fuels. And this is also something that is sort of pushing in the wrong direction with respect to the energy transition. This is sort of to give a general answer then, but to sort of specify every single trade relationship that we've considered, and so when considering if a country would trade with another, was taken into account these tariffs and non-tariff measures. And therefore, when you look at the Sankey diagrams and all of our trade results, they are in a way a result of the existing trade barriers that are in the world. I think this is as many questions as we can answer here live now. However, we have received several more, and we will follow up by email. So thank you very much for asking your questions. Thank you all. Thank you, Frank, for joining us today and for your insights and for all of the collaboration that we've had. Thanks to all of the participants, and I hope to see you in other IEA webinars if you are interested. Thank you very much. Goodbye.